Hello and welcome to this AIM and RAIN Alliance webinar on RAIN System Design Guidelines. AIM is the global industry association that connects, standardizes, and advances automatic identification technologies. The RAIN RFID Alliance is an organization supporting the universal adoption of RAIN UHF RFID technology, wireless technology that connects billions of everyday items to the Internet of Things, enabling businesses and consumers to identify, locate, authenticate, and engage assets. RAIN Alliance is a part of AIM Inc. To start, we have some housekeeping items to go over. First, you'll note that you are muted throughout the webinar. If you have any questions, you can send them to AIM Member Services via the chat option. We will answer as many questions as time permits after the presentation. Also, to all those who registered to today's webinar, we will have a recording available in the coming days and we'll email you that when it is available for viewing. Today's speakers are from Semiconductor. They are Debs Mackery, Business Development Director, and Joseph Preisheimer-Flugel, the EVP, CTO, and Business Manager for RFID and NFC. Debs, take it away.
Thank you, Mike. Hello, everyone. Thank you very much for joining the webinar today. Over the next 35 minutes, Joseph and I would like to talk about some of the factors affecting the overall system performances in current generation deployments, especially in the current generation RAIN and tags, RAIN RFID tags and readers. The presentation is divided in two parts. The first part would be presented by Joseph that would cover some of the key aspects of the RAIN System Guideline documents that is developed by the RAIN Alliance Network. The next part of the presentation would be given by me and would cover some practical know-hows to enable high-performance RAIN deployment. But before we begin, who are we? CISC Semiconductor is a leading global supplier of RAIN RFID and NFC measurement and test solutions. CISC was founded in the year 1999 and are managed by a team of international skilled experts. Over the last 2 decades, we have supported R&D teams, engineering teams, manufacturing teams through our innovative products and services. We are headquartered in Klagenfurt, Austria, with R&D offices in Klagenfurt and Graz, and also support our global customer base through our extensive sales partner network. I personally work for the company in North America, and we have a sales location here in Mountain View. We also pride ourselves to be a standardization leader worldwide. We actively participate in different standards bodies and make sure we enable seamless connectivity of all the connected items. We hope to empower our customers to achieve seamless connectivity of everyday items through our performance and conformance measurement equipment, through the services we offer in testing and verification, and above all, the standardization knowledge that we have gathered over the last 2 decades. To sum it all up, we believe in adding trust to the connected world. Now, may I request Joseph to take over the next few slides.
Hello to everybody also from my side. This is Joe speaking. So I'm involved deeply in RAIN Alliance and heading the technical work group for some while. And inside the technical work group, we had lots of discussion inside the work group, also coming from other RAIN discussions. And the topic is, there are too many combinations of regulatory environments and protocol settings. So FCC has different settings compared to ETSI, compared to Japan, China, Korea. So this topic was something, and then you can connect this with different protocol settings to make the optimized performance of the RFID in this frequency band. So as a consequence, this topic was addressed in the RAIN technical work group for some while. And coming with this, there was also continuing discussion on the RAIN RFID interface. This means Gen 2 ISO 18063 has lots of options, lots of features. There's a strong community who developed the standards over the last 20 years meanwhile. And we're very active in this and know all the background, all the stories. But more and more people join the technology. It's spreading widely. And so there's importance to basically describe, explain where these features come from, where the protocol setting come from, what was the idea behind. And then as a third point, probably 2-3 years ago, we started with the challenge that the RFID tags became better and better. This means they need significant less power. And as a consequence, the range gets further. But this is also then a topic in the system design, because if the tag is further away, it takes the signal much a further distance to come back again. And this is also a topic that needs to be addressed. So the RAIN System Design Guideline is basically a picture here, what we know from the RAIN environment. So we have the items, which are tagged with the tags. They are read by the reader. It goes through the software and the network. And the particular focus, so next, please. What we had here in the RAIN system, no, sorry, back. So then the RAIN System Design Guideline is definitely the point that we look on the AI interface. So this covers tag sensitivity, tag backscatter strength, tag population orientation, all are then also the radiated power, reader sensitivity, antennas, and interference. So this is really the focus on the RAIN System Design Guideline. There's not much that goes beyond this. Next slide. Good. One aspect here is the topic of radio regulations. I mentioned already in the introduction that the radio band and the RAIN protocol allows a couple of options. And what we developed here in the System Design Guideline is we gave them codes, and the codes should allow us to reduce the number of different settings. So I listed here a few of the famous ones or most popular ones. It's UA8A, which means European band in the 865. So the first two letters always means the country, the region. Then it's the main frequency band, so 800 or 900 megahertz band. And then it's just a sequence A, B, C, whatever is necessary. And in Europe, U8A is quite straightforward. We use it already for a significant while. Now we have in Europe the U9A and 9B. 9A is for 3 channels, 9B is for 4 channels. So if you have followed the discussion in Europe about the 950 megahertz band, basically in the European Union, it was concluded in order to allow some band from 915 to 921 also for railways, that only 3 channels may be used. This has been adopted meanwhile by a significant amount of countries, and they use 3 channels. However, the 915 to 921 megahertz band actually would allow 4 RFID channels, and there are countries in Europe that are outside the European Union that use the same CPD guidelines, so the same regulatory guidelines as the European Union, but they partly allow 4 channels. For that reason, there's a second option that is for 4 channels. Then we have the US band, and here, for instance, US and Canada using the same 902 megahertz band, and they have the same setting, although the legal background behind using this frequency band is different. Below are then some examples, a little bit deeply technically, but it's just to highlight, it's not only specifying the regulatory part, so it means typically the transmit bandwidth, so TXEW, but also what BLF or DRM, so whatever is recommended to be used in the RFID protocol based on the RAIN protocol. Some more details are available in the System Design Guideline. I don't want to go too much into details here, it's on all the acronyms, but just to give you an impression what the table is about it. Next slide, please. Sorry, yeah. And very important here, in Europe, we have now the new 900 megahertz band approved. So this means 50 recommendation 7003 has been published already a year ago. This is the legal background. And then we had lots of hurdles in getting the ECTS standard passed. Finally, it passed all the European loops and it's now released for approval ballot. Actually, it has been done yesterday. So this document is now in a 4-month ballot until early August. And assuming that we don't get much comments this time, this means this document will be available then in fall 2020. And then all the basics for the 915 megahertz band are really completely done. And just a side note here, this ETSI and 0228 standard took that long in this update because a significant number of new tests have been introduced, which is in particular relevant for the reader vendors. But you can look it up on the ETSI webpage and see the details. Next slide, please. Good. So protocol considerations. We spent a significant effort or content of the document on the session flags. So actually there are 4 session flags plus the select flags. Those flags are very important on how you implement an application. And this is addressed in the system design document in order to help people to understand how to optimize applications by appropriate use of those session flags. Then there is also a topic on these high sensitive passive tags and battery assisted passive tags. What is the impact on the session flags? What does it mean? Because they have a significant longer range. For the battery assisted passive tags, they basically don't lose power. So how to ensure that you can do a proper handling of those tags. Then request RAIN is a special topic with the advantages and disadvantages. And then in order to understand all this implementation, there are examples there that describe what happens. The examples describe the way how to do it, or also the traps you could get into if you do it in a different implementation, a different way, and the risk, what is involved. Next slide, please. Good. System performance, I already mentioned earlier. This is a topic that became more and more relevant. And so we have on the one hand side the forward link from the reader to the tag and the return link, the signal coming back. Below are basically the formulas, how this relates in principle with the relations. And on the forward range, we have the power that is the reader is allowed to send. This is typically set by regulations, radar regulations. So it's either ETSI, it's FCC. And then we have the second parameter, this is the tag read. Also the power that the tag needs to read, needs in order to be read. And so this is basically the operating power. And this defines the forward range as a consequence. And then we have the return link, where we have 2 parameters, the tag backscatter power, which is basically given by the tag chip. How is it capable to operate? Debs, could you click? Next. And then the reader receiver sensitivity. And this is the second performance parameter of the system that then defines the return link. So those 2 parameters are basically the parameters now defining the performance or the overall read range of an RFID system. In the next slide, I have an illustration on this one. So this is just an example on a read range for an RFID tag. So the forward range is like, yeah, it has a peak at 900 megahertz, around 15 meters. And the return range, which is defined by the backscatter power of the tag, but also by the reader sensitivity, is something different. So as a result, the minimum of both is the operating range. So it doesn't help you if the tag can do 15 meters and 900 megahertz, but the reader gap is basically caused by the issue that the reader does not have sufficient receiver sensitivity, means a range drop of 5 meters or nearly 40%. On the other hand, what you see on the left and the right is the tag gap. Here it's definitely the topic that the reader, the tag is limiting this. And to give some examples, so what we have here is, so if the reader sensitivity in this example is minus 75 dBm, we have 8 meters range, as you see it here. But if the sensitivity drops by 6 dB, you halve the range. If it drops by another 6 dB, it's only a quarter of the range. So this makes it very clear that the reader sensitivity gets very important here for these high-end tags. So finally, the topic here is the tag gap is the range loss caused by the tag. Minimum operating power limits. The reader gap is the range loss caused by the reader sensitivity. Certainly considering the backscatter power given by the tag. In the system design guidelines, this is clearly addressed. What are the issues? What are the background? And it is also referring to the standardized measurement methods on this, which is the ISO 18046-2 for the reader sensitivity testing and the ISO 18046-3 for the tag sensitivity testing. Those documents have been completed by ISO in the last couple of months, and they are currently used. It should probably also be mentioned that the test settings of ISO 18046-2 for the reader testing are also partly adopted by the ETSI EN 3208 for the reader, for now mandatory reader sensitivity testing. So this, I would like to give a brief overview what the RAIN System Design Guideline is about. And this time we have also lots of members of the RAIN group here. Thanks to all the RAIN members, the RAIN technical work group members for their input and their participation, and also for AIM to helping us to move this forward. I would like to hand back to Debs, please.
Thank you. Now let us look into some of the terms that Joseph mentioned earlier in the slide already, a bit more in depth. So I would focus the next few slides on the topic of system performance and some of the key terms that we need to be aware of. When planning for a RAIN RFID setup, the most common metric that we hear is the link budget. But what is link budget and why is it important? Link budget is a calculation of losses and gains of RF power in an RF system. It really helps us determine the overall power requirements inside the system and also pinpoint locations where a tentative failure might occur. The factors affecting link budget are tag sensitivity, backscatter power of the tag, maximum output power of the reader, reader sensitivity, and the environment in which the application is being deployed. The actual application space really contributes a lot to the system performance. Primarily, the distance from the reader antenna determines the path loss in the system, which is used in calculations that I'm going to show in the next few slides. Also, another example is interference. As an example, if there is any metal near a RAIN tag or a lot of tag population in a space, this could drastically alter the tag sensitivity, thereby leading to a failure. Another example is the inherent interference that may be present at a deployment location. For example, a cell tower close by or an RFID installation close by. Therefore, it is always recommended to understand the environment in which the RAIN system would be deployed and to do a survey. Even after all of this, we do see additional failures during the process of deployment. And at that point, we need to be aware of the protocol and the communication that goes on between a tag and a reader, either through a sniffing software or through other softwares available in the market today. Now, we are aware that both reader and tags talk in a typical RAIN RFID system. So we have got two separate lanes, forward and reverse, as it was explained earlier. Forward link is the reader to tag communication, and it is dependent on the power received by the tag to wake the tag up. As the equation here highlights, power of the tag received is equal to the sum of reader transmit power plus the path loss. The two main factors that affect the forward link is tag sensitivity and the transmit power of the reader, each of which have their own factors. As an example, tag sensitivity is dependent on the overall size of the tag, the IC used, the antenna orientation, and therefore having an idea about the kind of tag to be used for an application is critical. On the other hand, for a reader transmit power, the practicality and regulations play an important role. Practicality here would be the design of the reader itself, and the regulations, as explained earlier, would be what is the maximum output power that can be allowed from a reader. Now, in a reverse link, the tag modulates its antenna's load impedance to send that information back, more commonly as we know as backscatter power. And this could be calculated. It is dependent on the power received by the reader and can be calculated as indicated in the equation below. Now, reverse link is dependent on the backscatter power of the tag and reader sensitivity plus the modulation loss. To sum it all up, we could say that a minimum of both the forward range and the forward link and the reverse link determines the overall operating range of the tag, or more commonly that we call is the real range. This is the minimum of the forward and the reverse link, and as mentioned earlier, is dependent on the reader power and sensitivity, tag consumption, and the backscatter efficiency. So all in all, it is really critical that we need to understand the hardware we are using for a system application. A thorough analysis, check back is really required, wherein we get to see how they perform independently, as well as how the tags and the readers perform in combination. Another critical factor is the backscatter power quantification. A wrong quantification of backscatter power may result in an incorrect estimation of the total operating range of the tags, thereby resulting in a failure. Over the last few years, we have seen some kind of a discrepancy available into how the reporting of the backscatter power is done, and which has been now resolved with all the standardized method that is present. So we need to be aware of this and use the right method to measure the backscatter power. This would result in the correct selection of the RAIN and the reader combination, thereby ensuring that the RAIN system application works completely. Another term that we keep hearing often and has gained a lot of momentum over the last few years is what is reader-receiver sensitivity, and why is reader-receiver sensitivity so important? Reader-receiver sensitivity, by definition, is the minimum power required at the reader-receiver port, so to detect the incoming signal from the tag. With the increase of tag sensitivity over the last few years, there is also there's an increase in the development of readers with higher receiver sensitivity. But just measuring the receiver sensitivity of the transmit or over the transmit power of the reader may not be enough to determine the overall functionality of the reader. In general, the reader-receiver sensitivity is dependent on design choices, that is how it is used. For example, the transmit power, the oscillator inside, or the signal interpretation software of the reader. It is to be noted that reader sensitivity is not dependent on the environment of the application itself. The environment may affect the overall system performance, but not the sensitivity of the reader. So in conclusion, we have outlined 4 different parameters that affect the overall sensitivity of the reader, and they need to be considered while selecting the right reader for a system application. A, the transmit power of the reader. B, the backlink frequency. 3, the phase of the received tag signal. And finally, inappropriate antenna conditions. Now, in this particular example, you would look at a sensitivity variation that is dependent on the transmit power of the reader. In this example, we have selected two separate readers, and we measured the dependency of the transmit power over sensitivity through our test tool, RFID Explorer. As expected, due to the self-jamming feature of the reader, higher the transmit power of the reader was, lower its sensitivity was. And this was shown in both the reader sample 1 as well as in reader sample 2. Okay, the next factor we consider is the influence of the phase of the signal received by the tag. In this scenario, we have measured 5 different readers to log its performance over the phase at which the tag answer arrived at the reader receiver. In general, this variation does not seem to appear a lot in a lot of readers, but in many of the application failures that we have noticed over the years, that this appears to be one of the main reasons. In an application, as we are aware, the phase of the signal received by the reader is dependent on the reader to tag distance. Based on that, the signal that is received is either in the I channel or the Q channel of the reader, or even partly between the I and the Q channel. This is something we need to be aware of during system application and adjust accordingly. Now, if we go into these readings a little bit more in detail, so the reader 1 here on the top, which is indicated by the blue line, seemed to have a very strong sensitivity variation due to the received signal. We notice a difference of up to minus 66. So we notice a difference of up to 13 dB to 14 dB, which is actually quite a lot and can hamper correct, accurate application. Therefore, testing the sensitivity of the reader over its phase is required to make sure that the failure is not because of that reason. And okay, so the next factor that I have considered here is the backlink frequency. We are aware that RFID system is a non-synchronous system. The tag has its own oscillator, and therefore the backlink frequency of the tag sent would be different than that requested by the reader. So there may be a misalignment between what the reader expects and then what the tag sends out. In this particular example, I'm showing you a reader that was tested to a higher dependency on this factor. The target backlink frequency requested by the reader in this case was 320. If the tag answers at 280, so we manually switched it to see its influence over the entire link frequency. And when the tag answered at 280 kilohertz, which is about 15% of the receiver sensitivity, we noticed a change of 4 dB. Therefore, poorer the sensitivity of the receiver, higher the chances of a system failure. Although the RFID protocol allows some backlink frequency variation, BLF variation, it is dependent on the backlink, and this variation is dependent actually on the BLF itself. If I'm not wrong, it could be somewhere between 6% to 20%, and it is a factor to be considered while measuring sensitivity. Now, let us consider another example. Here, the sensitivity varied depending on the configuration selected. So in this case, the reader selected to be measured was the same, but we set it in different configurations, starting with BLF 40 till BLF 640. So the configuration of the BLF and the coding used in each of these scenarios were different. The variation between the 40 kilohertz to 640, we do see a distinct difference. And the result of the 640 kilohertz was, of course, in comparison, lower in sensitivity than the rest of the settings that we had measured. So the point to be remembered is that even if the reader has been tested on one single parameters for a system applications, depending on the final BLF that is selected or the coding that is selected, we need to be aware that there is a variation of sensitivity, and that also needs to be considered in the process of application. Finally, let us just look into the Smith chart. Ideally, the impedance needs to be perfectly matched and is indicated here with the green dot at 0.0. In reality, it is not. And the impedance of the antenna starts falling away from the center point. Here, in this particular example, it is indicated by the yellow dot. In addition, we also have other variations of the phase shifting that results in miscalculation or the results on variation in the return loss calculations that we see that is dependent on the phase. Therefore, for an accurate setup, it is recommended to evaluate the reader behavior and the inappropriate antenna conditions. Emulation of not perfectly matched antenna helps to determine the overall reader behavior, and we are confident about how the reader would behave in such conditions. These are replicating real life scenarios in the process of deployment. This kind of it also helps us to evaluate the effect of return loss on the reader sensitivity, thereby accurately suggesting how the reader would behave in case of different conditions. Moving on, finally, the protocol consideration. Joe has already spoken a bit about this earlier as to how important protocol is and what to consider, what are the sessions that are in there to consider. Now, considering the protocol is important for the success, and we all know that. As mentioned earlier, RAIN RFID protocol supports 5 different session flags, which have different characteristics. This provides a guideline as to how to use the reader and a tag in a given population. An example of this is in a static tag population, the reader needs to switch antennas or channels to provide diversity in order to energize and read all the tags. And we need to be aware of this during implementation. This is explained a bit more detailed in the system guidelines, and it would be recommended to read through the guideline to have a more variation. So I am not going to all through all these details. It is also be recommended to be aware of the detailed communication between the reader and tag. For example, we need to be aware of the query command sent or how the tags are behaving in different environments, which would be the protocol allows some kind of options, the backlink frequency for data rate as an example, or the command options. And we need to be aware of this, and this can be done when reviewed detailed between the tag and the reader communication. To sum it all up, the RAIN System Design Guideline is available on the RAIN under Resources, RAIN website under Resources, and it would be recommended to go through the document and have a detailed look into what is offered. There are a lot of solutions for easier deployments, and that might be helpful and a good starting stone to move on to your system applications. This is an active document, and we keep hearing comments, feedbacks, and other new topics that might come over, and we would be happy to add those in. So any kind of feedback or recommendations on how the document should develop, or if there are any feedbacks on the document, it would be great if you could reach out to the RAIN Alliance for this. We need to be aware that we have the code for the radio regulations already available. Joe has given a few examples earlier in the slide. This would really simplify the process of application. Hence, it's a good idea to have a look into these configurations and see how they might be helpful for the region in which the application is. And finally, we need to consider that the sensitivity of RAIN readers have to be improved, and also considered the fact that we are now in a stage wherein the ICs are really sensitive, so low power tags can provide better range. This has opened a new avenue of applications for us, but at the same time, new challenges that we are faced by the reader. So when selecting your combination of tag and readers, please make sure to go beyond the data sheet, beyond the numbers that are available, to run through few applications, test your tags on different parameters, as well as on test your readers on the different parameters that was explained earlier in this webinar. Thank you.
Thank you, Joseph and Debs. So we have some time for some questions if you are ready for that.
Yeah, sure.
Okay, great. The first question we have is, why is the return link so important? I always thought that the tag operating power is determining the range.
Joe, do you want to go for that?
Yeah, I mean, the return, also the backscatter power is that important because if you have a low power tag, what I mentioned earlier, you're getting further and further away from the reader, and the signal needs to go back a very long way. And for a low power tag, it's more difficult to provide more backscatter power. So the consequence is that you start with less power, you have a further way to go. And for that reason, the reader sensitivity becomes the very challenging topic. If you follow the RFID in the last 30 years, that's a long while, for HF system, it was always the return link that was the significant topic, or most time, especially for long-range HF systems. In UHF, we always started with the power. So when we started UHF 20 years ago, roughly, it was always the tag power consumption that had this limit. And this was, yeah, for more than 15 years the case, but around 3-4 years ago, when the new generations of tech came on the markets, like Monza 6, or UCODE 7, or EM Echo, or the latest Alien Higgs. This was the time where this changed because the tech improvement was so good, and now the challenging part is on the return link on the reader side.
Okay, thank you. The next question we have is, why should I analyze the protocol? It is anyways defined in the Gen 2 standards?
Yes.
I can take that. The protocol allows different options, as I was explaining earlier, some of them being the DLF for data read, or the command options on sessions flag and how they behave on all different parameters, and also how the commands are used in loops. As an example, how often should a query go out, or what query values should be used, what are the settings for that. So therefore, it is important whether the settings are allowed the way it is intended to. We need to make sure that the settings go in the intended process, and a protocol analysis is therefore significant for the software design and verification, and it can allow that. And hence, we need to consider the protocol even if we are aware of what the Gen 2 spec says.
Okay, thanks. And Debs, I think this one is kind of relative, and you might have answered it, but does this, or how does this affect the optional commands?
Joe?
Yeah. Does it affect the optional commands? It hardly affects the optional commands. The reason is that the optional commands are usually only then used once you have identified the tag already, you're in the open or secure state. So for this, in this case, it's really just about data exchange where the optional commands are used. It's a little bit different if you go for the battery assisted tags, because you have the flex query, which is basically part of the anti-collision, so the collision arbitration, where this gets important. But in summary, if flex query is seen like a query, then it's fine. But the optional commands usually just for data exchange and have a lower impact on the performance, except that they need time to execute them.
Okay, great. Another commenter said, thanks for the very clear presentation. Do we have to also consider the signal to noise ratio as a possible limitation to read range?
Yes, this is certainly a topic. It depends on the RF environment. I mean, the reader sensitivities are still in a range where there is room for improvement, room for handling this. So currently, I think the reader sensitivity is able to handle this, but if you have environmental noise because of other RF installations nearby, this is definitely impacting the system performance.
Great, thank you. And can you indicate if there is any impact when interrogating user memory versus EPC memory?
So far, what we have done as evaluation of tech performance testing, there's no difference on the current types of tags that are on the market.
Okay. Another question we have is, I am concerned about interoperability issue readers. Are all readers under EPC Global compliant RAIN?
The interoperability issue might be related to the regulatory environment, but I mean, GS1 definitely, so which means EPC Global definitely has a certification program for readers. And as RAIN RFID basically says, okay, the RAIN protocol is the EPC Gen 2 and the ISO 18006C or 63. There is nothing to be concerned in respect to the compliance. Interoperability is another topic because you can set up one reader that way, the other reader the other way, and they may interfere with each other or cause troubles, but this is a system design issue.
Okay, great. And another question we have is, multi-reader environments often create reader-on-reader interference for tags. How much does this affect real range?
Yeah, I'm in the topic for 20 years now, and it was a significant issue in the early days of RFID, even for the first Gen 2 compliant products. But what changed was that the industry got aware of this issue. So most tags have now, probably all tags have input filters. This means reader-to-reader interference in respect to beat nodes and something like that is an issue if you use channels that are close to each other. You can see that the minimum or the highest data rate used in the forward link is around 160 kilohertz. So those filters are designed, these are low-cost filters, so they typically filter out at around 1 megahertz, half a megahertz. So it's always recommended to have the reader channels which are close to each other, at least by 1 megahertz separated. This is from a practical experience. But however, if a tag receives commands from two readers at the same point, so they have really command interference, then it's really hard to resolve this. But if it's just the RF interference, then appropriate channel plan helps. In Europe, we definitely decided at this point that you have, for instance, lots of portals close to each other. You either select channel 3 and 10 for the portals, or you give them channel 7 and 13, so that every second portal has a channel which is 1.2 megahertz away from the other one.
Okay, great. Okay, and this question is, do you know some dual frequency RAIN tag with even NDEF area, something like EM4423 with both UHF and HF?
I'm sorry, I don't know what the term anti-EF area means.
Since I'm not too sure too, I would just suggest that the person asking the question could send an email to us.
I think they mean NDEF, Joe.
Okay. I can't answer this question directly now. I need to do some investigations.
Okay, great. And for our last question, Debs, you did say that people could potentially, submit comments on this document. How would they go about doing that?
I mean, the best way is to reach out to Joe. He is leading the technical work group in this case, and he would collect all the comments on this and go over the technical work group members.
All right, thank you. So that wraps up our webinar presentation today. Thank you so much, Joseph and Debs, for your insights. We really appreciate it, and we'd like to thank the audience as well for their active participation today.
Thank you. It was a pleasure. Thank you, everybody.
Thank you so much.